This is the first video on section 5.1, functions and level curves. Recall from Calc 1, generally on the first day, you see the definition of a function given fairly abstractly. It's just a rule that assigns each element of one set an element in another set, a unique element in another set. This set is called the domain. This set is called the codomain. And in Calc 1, we look at functions a little abstractly, usually the first day in the first assignment. And then after that, functions generally have their domain as subsets of the real line. In Calc 3, however, we're going to look at functions of different domains. So our functions here are going to go from Rn into the real line. Generally, n is going to be 2 or 3, however. So here's a function from R2 into R. And we want to find the domain and the range. By domain here we mean the natural domain. This is a second-degree polynomial. Now, polynomials in Calc 1, just polynomials of one variable, had their domain the entire real line. Here we have a function of two variables. Its domain is the entire plane, R cross R. Why? Well, as in Calc 1, sometimes it's easier to ask ourselves what's not in the domain. Are there any numbers we can't square? No. We can square any x, we can square any y, we can subtract any two numbers. So that's why the domain is all of R cross R. The range is the entire real line. This is a little bit more difficult to see. In general, range is a harder question to ask than domain. This is why. Range is a prediction. Domain is what you're going to, these are all the things you're going to plug into the function. Range are the things that can come out. So you're trying to anticipate a result. So that's what makes a range question harder in general. So we're claiming that the range is the entire real line. Let's see why. So let's take a z and r, and we want to find some pair in xy whose function value is z. The easier case is if z is greater than or equal to 0. If z is greater than or equal to 0, let's just consider its square root. And then we apply the function to the pair square root of z, 0. That gives us square root of z squared, which is z, because z is a positive number. If z is negative, intuitively I think we can see how to get the z back out of the function, but algebraically we have to be a little bit more clever, a little bit more careful. So we can't take a square root of a negative number. So we take its absolute value first. Then we take the square root. Then we have the point 0, or square root of absolute value of z that we substitute into our function. So what does this do? This is going to square this term, first of all, which will give us the absolute value of z. Then we multiply by -1, which will give us z in the case that z is negative. So what this statement says is, if z is a real number, one of these two function values is z. So either the square root of z squared is equal to z, or -1 times the square root of absolute value of z squared is z. One of those two is equal to z. For part B, f of x is a square root, or f of xy is a square root of x plus y. What's the domain? Well, we don't take square roots of negative numbers. So we need x plus y to be greater than or equal to 0. That means y is greater than or equal to -x. So our domain is a set of pairs xy in R cross R such that y is greater than or equal to -x. Our range are going to be non-negative real numbers. So the numbers greater than or equal to 0. For basically the same reason that when you looked at Calc 1 and you just looked at the square root function, its range was this. So we can see, first of all, no negative numbers come out. So the question is, how do we get all non-negative numbers out? Well, if we pick a z here, then f of z squared 0 is going to be z. Also, f of 0 z squared is going to equal z. These are just two ways to get z out. They're not the only two ways. So we're not claiming here that our function is one-to-one, because we have two different ways to get z out of our function. I've demonstrated two different ways. There are a few more.